All right, ready to dive into something truly mind-bending today?
Always up for a challenge.
Well, get ready, because we're tackling Quantum Singularity Unification Theory, or QSUT for short. It's a theory that attempts to explain, well, everything.
What's really fascinating about QSUT is that it proposes that everything we observe, even space-time and the fundamental forces, emerge from these tiny discrete units called quantum singularities.
It's like envisioning the universe as a giant Lego structure with these quantum singularities acting as the individual bricks. But instead of plastic, we're talking about the most fundamental units of energy imaginable.
That's a good way to visualize it. And just like with Legos, the way these quantum singularities connect and interact determines the structure and behavior of the universe.
So tell me more about these quantum singularities. What exactly are they? How are they different from, say, the particles we learn about in traditional physics?
Okay, so in traditional physics, we think of particles as points or sometimes as waves spread out over space. But QSUT says that's not actually the fundamental picture. Instead, it proposes that these quantum singularities, or QSs, are the truly basic building blocks. They're not points or waves, but something entirely different.
So instead of thinking about electrons and quarks, we're now dealing with these even more fundamental entities, these QSs, like we've zoomed in another level on a cosmic microscope.
Exactly. And what makes QSs so unique is that they have this property called a phase coherence parameter. Think of it as a sort of stickiness factor.
Stickiness.
Yeah, stickiness. It determines how strongly each QS interacts with its neighbors.
So a QS with a high phase coherence parameter is like a really sticky Lego brick. It wants to connect strongly with others.
Precisely. And the strength of these connections, along with the energy of each QS, dictates how space-time emerges from this network of interacting QSs.
Okay, so we've got these QSs, each with a specific energy and stickiness factor, and somehow their interactions create space-time. That's a big leap. How does that actually work?
Well, that's where things get really interesting. QSUT introduces this concept of a space-time emergence function. It's a mathematical formula that describes how the connections between QSs, influenced by their energy and phase coherence, actually define the distances between things, the flow of time, essentially, the fabric of space-time itself.
So instead of space-time being this pre-existing stage on which the universe plays out, it's actually emerging from the interactions of these tiny QSs. It's like the stage itself is being built as the play goes on.
Exactly. And it has huge implications for how we think about gravity and other forces.
I'm hooked. Let's talk about the forces. How does QSUT explain things like gravity and electromagnetism? Are they still fundamental forces in this picture?
That's where QSUT really diverges from traditional physics. Instead of being fundamental, forces like gravity and electromagnetism are thought to be emergent phenomena. They arise from the interactions of these QSs.
Emergent forces. So instead of being fundamental forces of nature, they're more like ripples in a pond caused by the pebbles of QSs.
That's a good analogy. Imagine a still pond, right? Now drop a pebble in. You get ripples spreading outwards. QSUT suggests that the interaction of QSs creates similar ripples, but these ripples manifest as electromagnetic and gravitational effects.
So instead of pebbles, we have these tiny quantum singularities. And instead of ripples on water, we have forces. It's like the universe is a giant quantum pond, and the forces we experience are just the ripples created by these QSs interacting.
That's the general idea. It's quite a different picture from the traditional view of forces.
I'm trying to wrap my head around it. Could you give me an example? How would this work for, say, electromagnetism?
Sure. Imagine each QS as a tiny source of electromagnetic waves. These waves spread out like ripples, and they can interfere with each other, just like waves in a pond. Now imagine countless QSs, all creating these overlapping waves. The resulting interference patterns, determined by how the QSs are arranged and interacting, would give rise to what we experience as the electromagnetic force.
So the electromagnetic potential, which governs how charged particles behave, isn't a fundamental field, but rather a consequence of these QS wave interactions. That's pretty different from traditional electromagnetism.
It is, and it leads to some fascinating implications, especially when we consider the early universe where these QS interactions would have been much more intense, much more dynamic.
So you're saying that the early universe with its dense concentration of QSs would have been a wild place in terms of electromagnetic interactions.
Exactly, and those early interactions could have left a lasting imprint on the universe, a fingerprint that we might be able to detect today in the cosmic microwave background radiation, that faint afterglow of the Big Bang.
Okay, that's electromagnetic forces. What about gravity? Does that work the same way?
Gravity is a bit different. Instead of being a purely geometric phenomenon like in Einstein's theory of general relativity, QSUT defines gravity as an emergent effect of how QS energy is distributed.
So clusters of QSs with high energy density would create a stronger gravitational pull. Like the more densely packed the Legos, the stronger the gravitational force.
That's the idea. And this leads to localized regions of gravitational distortion. We could actually observe those as imprints of early universe structure formation in something like the cosmic microwave background radiation.
That's incredible. So we're talking about a universe where even gravity, this seemingly fundamental force, is a consequence of these tiny interacting quantum singularities.
Yes, and that's just the beginning. QSUT makes a number of other predictions that could potentially be tested, some of which challenge our current understanding of the universe quite dramatically.
This is all incredibly fascinating, but I know that no theory is without its challenges. What are some of the hurdles that QSUT faces? What are the skeptics saying?
Well, the biggest challenge is the lack of direct evidence. We haven't actually observed these quantum singularities directly.
Yeah, that makes sense. If these QSs are the fundamental building blocks of reality, you'd think we'd have caught a glimpse of them by now.
Right. But remember, we're talking about entities that are far smaller and more fundamental than even the particles we study in particle accelerators. Detecting them would require technology and experimental techniques that are far beyond what we have today.
So it's a waiting game for technology to catch up.
In part, yes. But there are other ways to test the theory by looking for its indirect effects. For example, QSUT makes specific predictions about the patterns we should see in the cosmic microwave background radiation, and those patterns are something we can observe and measure.
So it's like looking for the footprints of a dinosaur. Even if we can't find the dinosaur itself, we can infer its existence from the traces it left behind.
That's a great analogy, and that's what physicists are doing with QSUT, looking for those telltale signs, those indirect pieces of evidence that support the theory.
Okay, so lack of direct observation is one challenge. What are some of the others?
Another big one is the mathematics. The mathematical framework for describing a universe built from interacting QSs is extremely complex and still under development. We're dealing with concepts like discrete, non-commutative geometry, which are incredibly challenging to work with.
So it's like trying to build a skyscraper with a blueprint that's still being drawn.
Exactly. It's a work in progress. But physicists are making progress, developing new mathematical tools and techniques to tackle these challenges.
It sounds like QSUT is really pushing the boundaries of theoretical physics. It's exciting to think about the potential breakthroughs that could come from this research, even if it takes time to fully develop the theory.
Absolutely. And it's important to remember that even the most successful theories in physics, like general relativity and quantum mechanics, faced skepticism and challenges in their early days. It often takes time for radical new ideas to gain acceptance, especially when they require us to rethink our most fundamental assumptions about the universe.
It's like when Copernicus proposed that the Earth revolves around the sun. It was a radical idea at the time, and it took a while for people to accept it. But eventually, the evidence became overwhelming, and the heliocentric model became the accepted view.
That's a great example. And maybe QSUT will follow a similar path, with initial skepticism giving way to acceptance as the evidence mounts and the theory matures.
Well, I, for one, am eager to see how this all unfolds. It's fascinating to think that we might be on the verge of a major paradigm shift in our understanding of the universe.
Me too. It's a truly exciting time to be involved in physics.
We've talked about the challenges, but I'm curious about the potential solutions. Are there strategies that physicists are employing to overcome these obstacles? What's happening on the front lines of QSUT research?
There's a lot of exciting work being done. On the experimental side, physicists are looking for ways to test QSUT's predictions, even without directly observing QSs.
So, like using existing experiments or telescopes to search for those telltale signs, those subtle effects that QSUT predicts.
Exactly. For example, one of QSUT's predictions is that the very early universe, dominated by these interacting QSs, would have been much colder than what the standard Big Bang model predicts.
A cold start to the universe. That seems counterintuitive.
It does, doesn't it? But QSUT suggests that the intense energy and interactions in this early QS-dominated phase wouldn't manifest as heat in the conventional sense. Instead, the energy was bound up in the fabric of space-time itself, in the very structure of these interacting QSs.
Okay, I'm following. But if the universe started out cold, how does that square with what we see in the cosmic microwave background radiation? Isn't that supposed to be the afterglow of a hot, dense early universe?
That's the interesting part. The variations in the CMB, those tiny temperature differences we observe, might actually match the interference patterns predicted by QS interactions in a cold universe. It's like those temperature fluctuations we see are actually a snapshot of the universe as it transitioned from this cold, quantum singularity-dominated state.
So instead of seeing the remnants of a hot Big Bang, we're actually seeing the universe emerging from this cold, QS-dominated state. That's a pretty wild idea.
It is, and if physicists can show that the patterns in the CMB match the predictions of QSUT, it would be a major piece of evidence in favor of the theory.
It's like finding a fossil that completely rewrites our understanding of evolution.
Exactly. And there are other avenues of exploration as well. Some researchers are proposing new experiments specifically designed to detect signatures of space-time discreteness at the Planck scale.
Okay, remind me, what's the Planck scale again?
It's the incredibly tiny scale where quantum gravity is thought to dominate. It's about 1035 meters, which is billions of times smaller than an atom.
Wow, that's tiny. So how can we possibly detect something happening at such a small scale?
It's incredibly challenging, but physicists are exploring various approaches. One idea is to look for what are called quantum foam effects in gravitational wave experiments. If spacetime is discrete at the Planck scale, as QSUT predicts, then those gravitational waves might exhibit tiny fluctuations or distortions as they propagate through this, well, grainy spacetime.
It's like listening for the subtle pops and crackles of a vinyl record, those imperfections that hint at the underlying structure of the medium.
That's a great analogy. And while detecting these quantum foam effects would be incredibly difficult, it's not impossible. Advances in gravitational wave astronomy might make such observations possible in the future.
So it's another waiting game, but this time for our instruments to become sensitive enough to detect these subtle effects.
Exactly. But in the meantime, there's another interesting approach being explored: condensed matter analogs.
Condensed matter. So
Yeah.
we're talking about solids, liquids, that kind of thing.
Well, more specifically, we're talking about systems like Bose-Einstein condensates, which are incredibly cold and coherent states of matter that exhibit some very strange quantum behaviors.
Okay, so like ultra-cold atoms behaving in weird quantum ways.
Yes. And the idea is that by studying these systems, we might gain insights into how space-time could emerge from the collective behavior of QSs.
So we're using these ultra-cold systems as stand-ins for the early universe to test some of QSUT's predictions.
That's the idea. Because if we can create conditions in the lab that mimic some of the key features of a quantum singularity-dominated universe, we might be able to observe emergent phenomena that support the theory.
Okay, I'm starting to see how physicists are tackling these challenges. What about the mathematical difficulties? Are there any strategies being employed to develop a more robust mathematical framework for QSUT?
Yes, there's a lot of work being done on that front, too. Some researchers are using what's called a lattice model to describe spacetime, where you imagine space as a grid of interconnected points rather than a continuous sheet. This helps to avoid some of the mathematical infinities that plague conventional quantum field theory when dealing with point-like particles.
So it's like those pixel art pictures again. But now we're using a mathematical grid to represent the fabric of spacetime.
That's a good way to visualize it. And this lattice model allows researchers to simulate the behavior of quantum singularities and see how they give rise to emergent forces and spacetime itself.
Very cool. So it's like using a powerful computer to run a virtual universe based on QSUT's rules and seeing if it matches what we observe in the real universe.
Exactly. And there's also a lot of effort being put into deriving the standard model's gauge groups, which describe the fundamental forces from the dynamics of the quantum singularity field.
So showing that the forces we know and love can naturally emerge from this sea of quantum singularities. Like, electromagnetism isn't a fundamental force, but rather a consequence of how these QSs are interacting.
Precisely, because if QSUT can't reproduce the standard model, which has been incredibly successful in describing particle physics, it's a pretty big problem for the theory.
It's like building a house. You can have the most beautiful blueprints in the world, but if you can't build the actual structure, they're just pretty pictures.
Exactly. It's amazing to think about it, Those tiny fluctuations in the cosmic microwave background, something we can actually measure, could hold the key to unlocking the secrets of these quantum singularities, the nature of space-time itself.
It's like we're peering back in time to the very beginning of the universe, trying to decipher the language of these ancient quantum singularities. But there's another challenge we haven't really touched on yet, right? This idea of reconciling QSUT with the standard model of particle physics. I mean, the standard model is like the reigning champion of particle physics. It's incredibly successful at explaining the behavior of all the known particles and forces.
Yes, that's crucial. Any new theory that comes along has to be able to reproduce the successes of the standard model, or at least explain why the standard model works so well in the domains where it's been tested.
It's like trying to create a new map of the world, but it still has to include all the cities and landmarks that we already know about. You can't just throw out the old map entirely.
That's a good analogy, and it's one of the key areas where QSUT researchers are focusing their efforts. They're trying to show how the particles and forces that we know and love, the ones described by the standard model, can actually emerge from the dynamics of these quantum singularities.
So it's not about throwing out the standard model, but rather showing that it's a kind of zoomed-out view, an approximation of a deeper reality that's governed by these quantum singularities. Like saying that the Earth looks flat if you're standing on it, but if you zoom out far enough, you see that it's actually a sphere.
Precisely. And there are a few ways that physicists are approaching this challenge. One is to look for what we call emergent symmetries. Symmetries are patterns that repeat themselves, and they're incredibly important in physics. They help us understand the relationships between different particles and forces.
So like the symmetry of a snowflake, or the way the two sides of a butterfly's wings mirror each other, those kinds of patterns.
Exactly. And in the standard model, symmetries are crucial for understanding the fundamental forces. What QSUT researchers are trying to do is show that the standard model symmetries might actually arise from the collective behavior of countless quantum singularities.
So instead of thinking about symmetries as fundamental properties of the universe, they're actually emerging from the complex dance of these quantum singularities. It's like those flocks of birds we see sometimes, where the individual birds are moving in seemingly random ways, but the flock as a whole exhibits these beautiful symmetrical patterns.
That's a great analogy. And it's one of the key ideas behind this concept of emergent symmetries in QSUT. If physicists can show that the standard model symmetries can be derived from the dynamics of the quantum singularity field, it would be a major step towards reconciling these two seemingly different frameworks.
It would be like finding a hidden code that translates between the language of quantum singularities and the language of the standard model. But symmetries are just one piece of the puzzle, right? What are some other strategies being explored?
Another approach is to look for what physicists call corrections. These are tiny deviations from the predictions of the standard model that might arise because of the discrete, granular nature of spacetime in QSUT.
So they're looking for tiny glitches in the matrix. Little hints that reality isn't as smooth and continuous as the standard model suggests.
Exactly. It's like looking for those subtle imperfections in a seemingly perfect diamond, the tiny flaws that reveal its true nature.
Okay, but if these corrections are so tiny, how can we possibly measure them? Wouldn't we need instruments with incredible precision?
Absolutely. We do need incredibly precise measurements. But luckily, we have experiments like the Large Hadron Collider, which is pushing the boundaries of precision measurement in particle physics.
So we might already have the data we need, hidden somewhere in those massive data sets generated by the LHC. It's like sifting through a mountain of sand to find a tiny grain of gold.
That's a good way to put it. And as our analysis techniques improve, and as the LHC continues to collect more data, we might be able to tease out these subtle signatures of QSUT.
Okay, so we've got these strategies for reconciling QSUT with the standard model. But there's also the issue of those anomalies we talked about earlier, right? The things that the standard model just can't seem to explain. Could those be clues pointing towards QSUT?
Absolutely. Those anomalies are like cracks in the foundation of the standard model. They're suggesting that there's something deeper going on, some new physics that we need to uncover. And QSUT might be able to provide the missing pieces of the puzzle.
Give me an example. What kind of anomalies are we talking about?
One of the most intriguing anomalies is in the behavior of neutrinos. Neutrinos are these incredibly tiny, almost massless particles that interact very weakly with matter. They're like ghosts that pass right through us all the time, without us even noticing.
Yeah, I've heard of them. They're produced in nuclear reactions, like in the sun, right?
That's right. And for a long time, physicists thought that neutrinos were completely massless. But in recent decades, experiments have shown that they actually do have a tiny bit of mass.
Okay, so tiny particles, tiny mass. What's the problem?
The problem is that the standard model doesn't predict why neutrinos should have any mass at all. In fact, according to the standard model, they should be massless. So the fact that they do have mass suggests that there's something missing from our understanding, some new physics beyond the standard model.
It's like finding an extra planet in a solar system. That's not orbiting the star in the way you'd expect. It suggests that there's some unseen gravitational force out there, something that's pulling the planet off course.
That's a great analogy. And in the case of neutrinos, this unseen influence could be the quantum singularity field. QSUT might be able to explain why neutrinos have mass, something the standard model can't do.
So QSUT is like a detective coming in to solve a case that has stumped everyone else. It's bringing a new perspective, a new set of tools to try and crack the mystery.
Exactly. And if QSUT can explain these neutrino masses, and if it can make other predictions that are consistent with what we observe, it will start to gain more credibility and acceptance within the physics community.
It would be like finding that rogue planet and then realizing that it's actually part of a binary star system with a second, hidden star that's influencing its orbit. It completely changes your understanding of the whole system.
Exactly, and that's the potential power of QSUT. It could completely revolutionize our understanding of the universe, reveal this hidden layer of reality that's been operating behind the scenes all along.
This is also mind-boggling. Are there any other anomalies that are giving the standard model a run for its money?
Yes, there are a few others. Another intriguing one is the measurement of the muon's anomalous magnetic moment. The muon is a heavier, unstable cousin of the electron.
Okay, another tiny particle. What's so anomalous about its magnetic moment?
The magnetic moment is basically a measure of how strongly a particle interacts with a magnetic field. And recent experiments have shown that the muon's magnetic moment is slightly larger than what the standard model predicts.
Okay, so another slight deviation from the expected value. But we're talking about incredibly precise measurements here, right? How can we be sure that this discrepancy isn't just experimental error?
That's a good question. And physicists have been incredibly careful to rule out all possible sources of error. The discrepancy has been confirmed by multiple independent experiments, and it's persisted even after accounting for all known uncertainties.
So it's looking like a genuine anomaly, something the standard model can't explain. And just like with the neutrino masses, could QSUT offer a potential solution?
That's what some physicists believe. It's still early days, and more research is needed. But the fact that QSUT might be able to explain these anomalies that have stumped the standard model is certainly intriguing.
It's like those old maps where the edges were labeled "Here be dragons." We're exploring the frontiers of physics, and we're starting to glimpse these strange and wondrous creatures that defy our current understanding.
That's a perfect analogy. And just like with those old maps, exploring these uncharted territories could lead us to incredible discoveries and a completely new understanding of the world.
Okay, so you've got neutrino masses, muon magnetic moments. Are there any other examples of these dragons lurking at the edges of our knowledge?
Well, there are a few other hints and anomalies that physicists are investigating, but those are perhaps the most prominent ones right now. And what's exciting is that QSUT, this radical new theory, might be able to provide explanations for these mysteries that have baffled physicists for decades.
It's like QSUT is a new lens that we can use to view the universe, one that might reveal hidden patterns and connections that we've never seen before. It's incredibly exciting.
It really is, and it highlights the fact that science is a process of constant exploration and discovery. We're always pushing the boundaries of our knowledge, challenging our assumptions, and seeking deeper explanations for the universe around us.
And sometimes those explorations lead us to completely new ways of understanding reality. It's what makes science so thrilling and rewarding.
I couldn't agree more.
Okay, this has been an incredible journey so far. We've delved into the challenges and potential solutions, and we've glimpsed some of the tantalizing anomalies that might point toward a deeper reality. Let's take another pause here to let all this soak in. When we come back, I want to talk about what this all means for us, for our understanding of the universe and our place within it.
Sounds good. I'm ready when you are.
We've gone deep into QSUT, explored its challenges, and uncovered some exciting possibilities. But let's bring this back to our listener. Why should they care about this mind-bending theory? What's the relevance to their everyday life?
That's a great question. On one level, understanding the fundamental nature of reality is a pursuit that's deeply human. It speaks to our curiosity, that inherent desire to understand how things work at the most basic level.
It's like we're carrying the torch from those ancient philosophers who pondered the nature of reality, right? They didn't have particle accelerators and telescopes, but that fundamental drive to understand the universe is still within us.
Exactly. And QSUT, with its unique proposition of a universe built from these quantum singularities, gives us a fresh perspective on those age-old questions. It challenges us to re-examine our assumptions about space, time, matter, even the very fabric of reality.
So it's about expanding our minds, pushing the boundaries of what we think is possible, appreciating the vast, unexplored landscape of the universe.
Precisely. But there's also a more practical side to QSUT. If it turns out to be correct, it could have profound implications for technology and our understanding of the universe's workings.
Okay, now you've got my attention. Practical implications. Tell me more.
For example, if spacetime is truly discrete, as QSUT suggests, it could open up entirely new possibilities for computation and information processing.
So, like quantum computers, but taken to a whole new level. Harnessing the power of those space-time pixels, those fundamental units of reality, to carry out computations that are impossible for our current technology.
Exactly. And it's not just limited to computation. Imagine if we could understand how gravity emerges from these quantum singularity interactions. That could lead to breakthroughs in energy production, new propulsion systems, even the potential to manipulate space-time itself.
Whoa, hold on. Manipulate space-time. Are we talking warp drives and time travel here? That sounds like science fiction.
Well, those concepts are still firmly in the realm of science fiction for now. But if QSUT is correct, it suggests that the laws of physics might be more malleable than we currently understand.
So the universe is more like a ball of clay that we can mold, rather than a solid block of granite.
That's a good analogy. And while we're still a long way from being able to manipulate space-time in such profound ways, the very idea that it might be possible is incredibly exciting.
It's like those early days of electricity, when people were just starting to experiment with it. No one could have predicted the incredible technological revolution that was about to unfold. Maybe QSUT is the spark that will ignite a similar revolution in our understanding and manipulation of the universe.
Maybe so. It's certainly an exciting prospect. But let's be realistic. We've talked about the challenges, the skepticism, the need for that undeniable evidence, the smoking gun. What are the chances that QSUT will actually pan out? Is it just a pipe dream? Or is there a real possibility that this could be the next big thing in physics?
Yeah, I'm curious about that too. What's your take on the future of QSUT?
Honestly, it's hard to say for sure. It's a relatively young theory, and there's still a lot of work to be done. But I think it has tremendous potential to be truly revolutionary.
So it's a long shot, but one worth taking.
Absolutely. And here's why. QSUT tackles some of the deepest mysteries in physics. The nature of space-time, the origin of gravity, the unification of forces. These are questions that have puzzled physicists for centuries. And while QSUT may not have all the answers yet, it offers a fresh perspective, a new way of approaching these fundamental problems.
Like a breath of fresh air, right? A new way of looking at the universe that might just unlock the secrets that have eluded us for so long.
Exactly. And even if QSUT doesn't turn out to be the ultimate theory of everything, the exploration of these ideas, the challenges it poses to our assumptions, will inevitably lead us closer to the truth.
And that's really what science is all about, isn't it? It's about pushing the boundaries of knowledge, exploring the unknown, and constantly questioning our understanding of the universe. And the scientists who are working on QSUT are clearly passionate about these ideas. They're not afraid to challenge the status quo and explore the frontiers of knowledge. That's what drives scientific progress.
I couldn't agree more. And it's important to remember that science is a collaborative effort, a journey that we all share. Whether you're a physicist working on the latest theories or someone who's simply curious about the universe, we're all part of this grand adventure of discovery.
It's a reminder that anyone can contribute to the scientific endeavor, right? Whether it's by asking questions, sharing ideas, or simply being open to new possibilities.
Exactly. And who knows, maybe one of our listeners will be the one to make that groundbreaking discovery, find that smoking gun that confirms or refutes QSUT. Or maybe they'll even come up with a whole new theory that revolutionizes our understanding of the universe.
That's an inspiring thought to leave our listeners with. So to everyone out there, keep questioning, keep exploring, keep pushing the boundaries of what you think is possible. The universe is full of mysteries waiting to be uncovered. And who knows what incredible discoveries await us just around the corner.
It's been an absolute pleasure exploring the intricacies of QSUT with you and our listeners.
Thanks for joining us on this deep dive. Until next time, keep looking up at the stars and pondering the mysteries of the cosmos.
And keep listening to The Deep Dive. We'll be back soon with another mind-bending exploration of the universe and its wonders.